Hello and welcome to the feature presentation. In this presentation, we're going to be covering a catalog of derivation operators. We're going to start with the concept of an ordinary derivative and work our way up to infinity categorical derivations. Let's begin. Before we head into this, it's important to call out this disclaimer. This presentation quickly jumps to higher mathematics and is not intended to be a proper lecture on the means of utilizing any of the presented material. This is purely for a conceptual introduction to a vast number of ideas that spawn from deeper studies in the differential calculus and theory of integration. While a fair understanding of basic calculus and linear algebra will be highly beneficial to those wishing to mathematically process information, the goal here is to allow the audience to dive directly into the many theorems that encompass the narrator's personal favorite area of mathematical study, that being differential geometry, biased by the motivations that yielded interest to this very study in the first place, such as mathematical gauge theories and theoretical physics. This is only to show that these concepts exist and that they are all related. The theories of differentiation and integration are sufficiently developed in the modern age, such that the entirety of calculus naturally falls out of the studies of either one of those processes, no less the case where these processes are forged into equality under Stokes-Cartan theory. In extension, this video not only covers the topic of derivation under the purview of real and complex analysis, but also proceeds to theorems within hypercomplex analysis, functional analysis, abstract algebra, cohomology theory, operator algebras, and category theory. Feel free to skip ahead in the video if you are ready to jump right into the vast theory of derivation operators. But if you are short on time and are interested in getting a summarization of all the operations covered in this video, I will go ahead and list them here while providing a simplified explanation of each concept. We'll start with what I call elementary derivatives. In section 1a, we begin with the concept of the derivative of a function in respect to a single real-valued variable. This is called an ordinary derivative. This should require little introduction. Moving on to section 1b, partial derivatives extrapolate our ability to take derivatives of functions that rely on multiple variables. This gives us a list of derivatives that distinguish between unique directions of derivation. Gradients encapsulate the partial derivatives of a multivariable function in a single vector, called a covector or dual vector. Meanwhile, directional derivatives play the role of selecting which direction one wishes to perform derivation in regards to using the information yielded by the gradient operator. The divergence of a vector field determines the tendency of a source or sink of vectors to occur about a particular location on a manifold. The curl operator then determines the means at which a collection of vectors have a tendency to rotate about a location on a manifold. The Laplace operator is a sum of second derivatives that determines the natural curvature of a function, vector field, etc. on a manifold. The D'Alembert operator is a spacetime derivative for a flat Lorentzian geometry called Minkowski spacetime. It is a composition of a time derivative, of course multiplied by a scaling factor with the speed of light, in addition to a Laplacian. Whether or not spatial derivatives or the temporal derivative obtain a negative or positive sign is determined either by personal choice of Lorentzian metric signature or the signature given by the basis vectors of a particular spacetime algebra. The Jacobian takes all derivatives of a function and composes them into a single matrix of arbitrary dimension. By taking the Jacobian of the gradient operator, we obtain the Hessian operator, expressing the curvature of a matrix-valued function in any dimension. Holomorphic derivatives, quite simply, extend derivatives of real-valued functions to derivatives of complex-valued functions that obey the Cauchy-Riemann equations, called holomorphic functions. Wirtinger derivatives extend this even further by considering both those complex derivatives that obey the Cauchy-Riemann equations as well as those that do not. This then establishes the notion of anti-holomorphic derivation. Now we cover what I consider to be non-elementary derivatives. These are a collection of derivatives that require more information than what has been established by elementary calculus of real and complex variables. We start with the Laplace-Beltrami operator, which is a derivative of a scalar function on a Riemannian manifold, which itself is a curved geometry. This means we rely on the concept of a metric to make sense of the derivative. This leads on to connections and covariant derivatives, where covariant derivatives rely on the concept of a connection to make sense of the notion of derivation. These are a sum of partial derivatives as well as connection coefficients that correct the way in which a vector transports across a curved manifold. Christoffel symbols of the second kind that are symmetric in their lower indices are added to partial derivative operators in order to establish the Levi-Civita connection, though other connections will be shown in the video. Lead derivatives measure how a function, vector field, or tensor field changes due to the flow generated by another vector field. A Lie algebroid derivation is a derivative of a vector bundle over a smooth manifold, given that the vector bundle is composed of properties that form a Lie algebra. The exterior derivative is a derivation that increases the degree of a differential form by 1, whereas the codifferential lowers the degree of a differential form by 1. They compose unique examples of the DRAM complex, expressing the topological and algebraic properties of derivation operators acting on algebras. Dolbeault operators extend the notion of exterior derivatives to complex-valued manifolds. A Hodge Laplacian then utilizes these operators to generalize the concept of the Laplacian to these complex-valued manifolds. This leads us to the idea of Dolbeault cohomology being a special case of DRAM cohomology. Geometric derivatives generalize the notion of derivatives to the study of geometric algebra, where we can compose ideas such as interior and exterior derivatives, as well as a space-time derivative that can operate on Lorentzian pseudo-Riemannian geometries. Exterior covariant derivatives add connection coefficients to the exterior derivative, extending it to differentiable manifolds and Riemannian geometries in general. Frechet derivatives allow us to extend the notion of derivation to normed inner product spaces, such as Hilbert spaces, where a limit exists uniformly for all directions. In finite dimensions, the Frechet derivative leads us to the ordinary derivative. A Gateaux differential is a version of this derivative that does not rely on a limit existing uniformly for all directions. Functional derivatives are a generalization of the ideas just mentioned to the case of functionals as a general study. In fact, the Frechet derivatives and the Gateaux differential are instances of functional derivatives, as they can operate on functionals. Therefore, this section will focus largely on the notion of variation, wherein we introduce the variational operator detecting infinitesimal transformations of an action functional. Dirac operators extend our ability to perform derivations on spaces that may be composed of spinor fields, where we can also consider the notion of spinor fields and gauge fields on curved spacetime. The Dirac operator relies on the Dirac gamma matrices to encode rotational symmetries in a spacetime, and the square Dirac operator then expresses the Riemann curvature tensor components acting on a spinor field, often in addition to the gauge field components of a gauge theory. Fueter operators are a special case of the Dirac operator, where we focus on derivations within the context of quaternionic functions in particular. As such, the Fueter operators can be interpreted as four-dimensional Dirac operators. This leads to the Cauchy-Fueter chain complex as a special instance of Clifford cohomology. Virasoro operators then extend our ability to perform derivations within the context of conformal field theories, where angles are preserved across scales. They are essentially a complex-valued extension of the covariant derivative to Laurent polynomials that, upon the action of derivation, form a Witt algebra with the addition of a conformal weight. This weighted Witt algebra is called a central extension, and in particular is called the Virasoro algebra. We now move on to operators that stretch beyond traditional intuition into fields of modern study. This leads us to highly abstract theories that can only be lightly touched upon within this video. H derivatives, called finite difference derivatives, stem from the notion of derivations in the context of discrete calculus. Q derivatives, on the other hand, also called Jackson derivatives, stem from a more particular study of quantum algebras and quantum calculus. If H derivatives stem from the realm of additive increments, then Q derivatives can be argued to stem from a realm of multiplicative parameters. These are both derivatives that do not rely on the notion of a limit existing whatsoever. In fact, applying an appropriate limit to each of these derivatives gives back the definition of the ordinary derivative. Fractional derivatives, such as the Riemann-Liouville or Caputo fractional derivatives, are derivatives that do not require integer order differentiation. We can have notions such as the half derivative of a function or the pi times ith derivative of a function. This then extends the concept of integration as well, which is actually what we will start out with in this section before properly introducing fractional derivatives whatsoever. Hausdorff derivatives are derivatives along fractal spaces, generalizing the concept of a Lebesgue measure to spaces where dimensions themselves may be of non-integer order. Differential graded algebras are derivations on graded algebras, such as a derivation on a tensor algebra. The nature of cohomology groups really begins to shine within the modern notion of a differential graded algebra. Quasi-derivations generalize what we learn from differential graded algebras to cases that may not be strict derivations, such as in the case of deformed algebras. A quasi-derivation is essentially the exterior derivative of deformed algebras. An operad plays the role of assigning graded vector spaces as a total set. Algebras of associative operads are called associative algebras, where algebras of commutative operads are called commutative associative algebras. This can continue on to other types of algebras, such as the idea of Lie algebras, which is an algebra of a Lie operad. We begin the section of derivation functors by building up the basic ideas of a category in terms of functors, generalizing the idea of homomorphisms. We then consider continuously deformable functors and derivatives of such functors. We then show other representations of the concept of a derivative that can be formed by the idea of a tangent complex and its relation to the cotangent complex. This shows that we can interpret derivations as homomorphisms from a complex into modules, where modules extend the definition of a vector space to rings as opposed to just scalars. Finally, I covered the generalized derivation functor, the cotangent and tangent chain complexes that are formed, and then the notion of a differential combinator, which is our last generalization of the concept of a derivative. Ordinary derivatives refer to the set of all derivatives that are elements of ordinary differential equations, expressing the rate of change of a function with respect to a single variable. Composing these derivatives with the operation of addition forms the most basic case of a space of linear differential operators. It is standard to define the ordinary derivative using the limit operator. This yields a derivation on a single variable function, as taught in a first course of calculus. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. The way in which we write the single variable derivative here in terms of a prime function of x is referred to as Lagrange notation, but we could have selected another notation. So equivalently, we could have written f prime of x as the derivative operator acting on f of x, where the derivative is being taken in respect to x. If we take a second derivative, we get the following. And then a third. In general, an ordinary derivative of order n can be written as follows. This is called the nth derivative of f in respect to x. Before moving on to partial derivatives, we will consider one final aspect of ordinary derivatives, leading to a trend of logic that carries throughout the study of differential operators. Ordinary derivatives operate on functions with the following linear map defined on the real numbers. F maps the real numbers back to themselves. In this specific case, we obtain the slope of a line tangent to the function being derived, which can be expressed by a smooth function f, smooth manifolds m and n, as well as the tangent space, in this case a tangent line, at a point P labeled T sub P, for which the derivative is generalized by the notion of a differential. Here's an example of such a tangent line for the function x squared. So as to not restrict our calculus of differential operators to only single variable functions, we acknowledge that the field of real numbers are not restricted to single variable representations. We can also have multivariable functions existing in vector spaces, such as R2 and R3, for example. We can massage our notion of differentiation to accept those functions that constitute the inherently richer algebras made possible by higher dimensional Euclidean spaces. In the three-dimensional Euclidean vector space R3, we are provided the ability to take derivatives in respect to three variables, represented in our example in terms of Cartesian coordinates x, y, and z. That is, given a function of three variables f of x, y, and z, which can be vector valued, we inherit three possible directions for which to take derivatives. In this case, a derivative in respect to x, in this particular case a partial derivative in respect to x, a partial derivative in respect to y, and then a partial derivative in respect to z. If we were in R2, we would only get two derivatives in this case. If we were in R4, we get four, so on and so forth. Partial derivatives are the backbone of partial differential equations, allowing us to begin considering a wider range of problems as they pertain to the algebra of physical space, and of course other vector spaces for which smooth manifolds can be defined. As a result, we can obtain unique derivation operators that establish rich behaviors that were simply not possible in the single variable case. Consider, for example, mixed partial derivatives, which can already be generated by second-order operators in R2 alone. The order of partial differentiation is commutative as well, establishing Clairaut's theorem. So the second derivative of a function in respect to x and then in respect to y is the same thing as the second derivative of f in respect to y and then in respect to x. The indices are commutative for these partial derivatives. So in this particular case, taking the second partial derivative of f in respect to x and in respect to x again is just the same thing as taking the second partial derivative of that function in respect to x. Second-order partial derivatives alone are sufficient to define the notion of a function's curvature in Euclidean space. This is important for the motivation of operators such as the Laplacian later on. When we had single variable functions in terms of f of x, we only had one unique derivative at first order. Say we have a polynomial function f of x equals 2x fourth plus 6x squared plus 18x plus 1. The ordinary derivative of this function is given by the following via the power rule and property of linearity. We obtain 8x cubed plus 12x plus 18. However, say we have a multivariable function f of x, y, and z equals 2x to the fourth plus 6y squared plus 18z plus 1. We can then calculate three separate derivatives, showing us the necessity of partial derivatives for different directions of derivation. Now we wish to consider an operator that contains all partial derivatives of a space as a vector. This leads us to the concept of the gradient, which we will cover next. Our ability to take derivatives of functions is expanding, but now we wish to combine everything we have already seen into a linear vector-valued operator, which we will call the gradient, labeled del. In R3, we have the following. We have the collection of these three partial derivatives, and allowing our function to once again be f of x, y, and z equals 2x to the fourth plus 6y squared plus 18z plus 1, we can calculate its gradient to form another vector in R3 called a dual vector or covector. By taking the dot product of this gradient with a particular vector, we obtain the directional derivative of a vector-valued function in the specific direction of that vector. So the directional derivative uses the dot product to select components of the gradient as needed. In the x direction, for example, we have the following directional derivative. This just yields the partial derivative of f in respect to x, since we are only deriving in the x direction. We have a much more powerful method for taking derivatives now that is capable of working with a wider range of functions that are potentially vector valued. The gradient provides the direction of steepest ascent for a function, while a negative gradient provides the direction of steepest descent. The directional derivative then plays the role of analyzing the sensitivity of a function's output to changes in different directions. In physics, all of these are crucial for measuring field strengths, heat flow, diffusion, and much more. Let's consider two more types of derivatives we can extract from the gradient operator composed with operations from linear algebra. Our first example here will be to take the dot product of the gradient operator itself with a vector field f equals p, q, and r. This leads to a scalar measure of the net outflow of a vector field at a given point, a positive outflow indicating a source, while a negative outflow indicates a sink. We refer to this as the divergence of the vector field. In this case, we just have a sum of first-order partial derivatives. The next example will be to take the cross product of the gradient operator with the vector field. Since f is in R3, we obtain another vector in R3 that measures the rotation of a vector field at a given point, and we call this the curl of the vector field itself. As you can see, this is clearly a more complicated calculation. Recall from earlier our discussion on how second-order partial derivatives were important for measuring the curvature of a function. Now we will see how this is especially true in the case of the Laplace operator, often referred to as the Laplacian. To form the Laplacian, we take the dot product of the gradient operator with the gradient of a function. In R3, this gives us the following set of second-order partial derivatives. The Laplacian of a vector field f is another vector field. In effect, the Laplacian measures the tendency of a function or vector field to curve from an average value. We can extend the power of the Laplace operator by generalizing it to a derivative that operates on Minkowski spacetime. For time and space to be given equal footing, we rely on a negative sign as well as a constant, the speed of light, for the time component. This derivative for a flat spacetime is called the D'Alembert. So we have negative 1 over c squared, c being the speed of light in a vacuum, times the second partial derivative of f in respect to time, plus the Laplacian of spatial coordinates. So this is a spatial Laplacian that's del squared acting on f. This is particularly useful in cases of special relativity, where time and space are on the same footing, giving rise to extraneous phenomena such as length contraction and time dilation. This can thus be modeled using the Minkowski metric tensor components. We use a negative 1 plus 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 signature in this case, which would be called a mostly positive signature, but we could have chosen a positive signature on the time derivative, and then the spatial derivatives would then be all negatives. So then our Minkowski metric tensor components would then be positive 1, negative 1, negative 1, negative 1 down the diagonals. We can also write the D'Alembert as follows. We can contain all first-order partial derivatives of a vector-valued function f with components f sub 1, f sub 2, etc. in a single matrix that measures the local behavior of that vector-valued function in n dimensions. This is called the Jacobian operator. To To measure the curvature of a real-valued function f in n dimensions, we can contain all second-order partial derivatives of the function in a single matrix called the Hessian operator, which, as a result of Clairaut's theorem, is equal to its own transpose. The trace of the Hessian matrix is the Laplacian. Likewise, if you already have the gradient of your function, you can take the Jacobian matrix of it to then obtain the Hessian. Until this point, we have concerned ourselves only with those functions that are real valued. Now we will focus on complex valued functions with the following linear map, where f maps the complex numbers back to the complex numbers. Holomorphic derivatives are complex analytic analogs of partial derivatives, intended for functions that are complex differentiable at every point in their domain. Consider the function f of z equals u of xy plus I times v of xy, where z is the complex variable x plus iy. A function f is holomorphic if it satisfies the Cauchy-Riemann equations. So the partial derivative of u in respect to x must equal the partial derivative of v in respect to y, while it's simultaneously true that the partial derivative of u in respect to y is equal to the negation of the partial derivative of v in respect to x. The holomorphic derivative is then given by the following. So you can write this as the partial derivative of u in respect to x plus I times the partial derivative of v in respect to x, or equivalently as the partial derivative of v in respect to y minus I times the partial derivative of u in respect to y. These derivatives are important for conformal mappings, wave functions in quantum mechanics, signal processing in electrodynamics, and much more. We can also consider a similar operator that does not require the function to be holomorphic, which is what we will cover next. We can take derivatives in a similar way for those functions that may not be holomorphic, e.g. they're not solutions of the Cauchy-Riemann equations. These are called anti-holomorphic functions. Consider the function f of z and z bar equals u of xy plus I times v of x and y, where z equals the complex variable x plus iy, and z conjugate equals the complex variable x minus iy. We can take not only a partial derivative of the function in respect to the complex variable, but also a partial derivative in respect to its conjugate. The combination of these derivatives are called the Wirtinger derivatives. These can be unified in a single operator equation in terms of complex conjugation. So if you have the derivative in respect to z, taking the conjugate of that whole derivative is equal to taking the partial derivative in respect to the conjugate of a function. With our operator notation, we conveniently take note that these operators are a simplified case of Dolbeault operators that are limited to acting on functions defined on the field of complex numbers. We will cover the Dolbeault operators later. We can extend the concept of a Laplacian to operate on Riemannian manifolds, particularly within the context of scalar fields on curved manifolds. First, we must define the Riemannian metric tensor G for this space. It is equal to the metric tensor components G sub mu nu times the tensor product of the differentials dx mu and dx nu. It is also symmetric in its lower indices. And importantly, its determinant is non-zero. This rank 02 symmetric tensor helps define the notion of distance on a Riemannian manifold, such as for a curved spacetime. Another common name for the metric tensor of a surface of a Riemannian manifold is the first fundamental form. With the given metric, we can define a derivative for a scalar field f on Riemannian manifolds, and this derivative is a generalized Laplacian called the Laplace-Beltrami operator. We now wish to consider vector fields and tensor fields on Riemannian geometries. To do this, we can begin with the idea of adding a connection condition to the partial derivatives that act on a Riemannian manifold, allowing us to perform derivations on a wider range of mathematical objects. We obtain a torsion-free, metric-compatible connection by using Christoffel symbols of the second kind, which are symmetric in their lower indices, defined by the following in terms of the inverse metric tensor components g upper sigma lambda times the derivatives of the metric. We can define the covariant derivative of a vector field f along another vector field x in the context of the Levi-Civita connection, which is covariant in respect to local changes in coordinates. With this connection condition, the covariant derivative components are given by the partial derivatives of the vector field plus the Christoffel symbols acting on the vector field. We can also consider the rank 3 torsion tensor T of x and f. Its specific formulation we won't cover in much detail right now. That will require understanding the Lie derivative in Lie brackets. If the torsion tensor is non-zero, we include an additional term for torsion components, expressing a more general affine connection. So we start out with the general same form, that is just the covariant derivative, but the actual components now are unique. There are other selections we could have made for the connection. Two will be listed here. We could have used spin covariant derivatives, or we could have selected a gauge to determine our connection condition. So a partial derivative operator is a limit of the covariant derivative where connection coefficients go to 0. Finally, taking the trace of a second-order covariant derivative yields the Laplace-Beltrami operator. If we wish to consider how a function, vector field, or tensor field changes due to the flow generated by another vector field, we rely on the Lie derivative, which incorporates derivative operators in Lie brackets. This was hinted at when we covered the torsion tensor on the section of covariant derivatives. In this particular case, we have the derivative in the direction x of f minus the derivative in the direction f of x. The Lie bracket endows the smooth sections of a tangent bundle with the structure of a Lie algebra. A Lie derivative is a special case of a Lie algebroid derivation when the algebroid is given by the tangent bundle itself. And in general, a Lie algebroid is a vector bundle A over a smooth manifold M, given that 1. The space of sections gamma of A is a Lie algebra composed of smooth vector fields on the bundle, meaning it is equipped with a Lie bracket. 2. There is a vector bundle morphism called the anchor map ρ, mapping sections of A to sections of the tangent bundle Tm, and it also respects the Lie bracket. For a function f that's an element of the space of infinitely differentiable functions on the manifold M, and S, which is an element of the space of sections, a Lie algebroid derivation D is then given by the Leibniz rule. At this point, we have come across some abstractly powerful derivation operators. However, we can compactify everything we have covered thus far and so much more by considering the exterior calculus of differential forms. In terms of integration theory, a differential form is an object that can be integrated over a manifold. Think of the differentials that occur under an integral, or those formed by the process of differentiating a function. For example, if a zero form is a smooth function, then a one form could indicate a line integral. Two forms would then integrate area or flux integrals. Three forms would indicate volume integrals, etc. A space-time integral would then be an example of a four form. A differential k-form omega can be expressed in terms of coordinate differentials by the following. The wedge product, also called an exterior product, is anti-commutative. So the wedge product of alpha and beta is equal to negative beta wedge alpha. The exterior product of two k-forms is a single k plus 1 form, so the exterior product increases the degree of a k-form by 1. However, we can inherit the notion of anti-commutativity through the definition of what we call the exterior derivative, which raises the degree of a k-form by 1. The exterior derivative is nilpotent, showing that the exterior of the exterior is equal to 0. We will consider the exterior derivative of a function in R2, such as f of x and y equals e to the 2x plus the tangent of y. The exterior derivative of any function f in R2 is first given by the following. So now we just compute the partial derivatives. For the specific function f of xy listed above, we then obtain the following. We get 2 times e to the 2x dx plus the secant squared of y dy. This is still a 1 form. But notice that f of x and y, a 0 form, was a smooth function. That is an example of a 0 form. The result we yielded under exterior derivation gives us a 1 form, since each term gives a single differential. The dimension of the function itself determines the amount of 1 forms that we sum to yield the total 1 form. Since we started with a single 0 form in R2, we obtain a sum of 2 separate 1 forms. However, let's now consider a function in R3, such as the case of f of x and y and z is equal to x cubed plus e to the negative y plus the sine of z. The exterior derivative of any function f in R3 is first given by the following. And of course, now we just compute those partial derivatives, piece by piece. For that specific function in R3, we obtain the following. We get 3x squared dx minus e to the negative y dy plus the cosine of z dz. We can test for nilpotence by taking the exterior derivative of df itself. But due to the nature of anti-commutativity, all of these differentials cancel out, showing us that once again that the exterior of the exterior must be equal to 0. This holds for all dimensions in all forms. We can generalize the fundamental theorem of calculus to manifolds of arbitrary dimension. Consider Green's theorem, the fundamental theorem of calculus for line integrals in 2D. Let omega equal a dx plus b dy. The exterior derivative of omega is then equal to the exterior derivative of a times the exterior derivative of x plus the exterior derivative of b times the exterior derivative of y, a wedge product being assumed. So dx dx and dy dy must go to 0. Let's switch the order of addition to make it look similar to the right-hand side of that integral equation. And now if we switch the order of dy with dx, we can pick up a minus sign. Next, all we have to do is organize and simplify as follows. Keeping in mind, there is an implied wedge product between these differentials due to their anti-commutativity. But now we see that the integral of omega is equal to the double integral of d omega. In R2, omega is a differential 1 form, so then its exterior derivative ought to be a differential 2 form, but that's exactly what we see with the double integral. In R3, omega then is a differential 2 form, whereas its exterior derivative must then be a differential 3 form. This generalizes the fundamental theorem of calculus to n dimensions. In this case, we have it in 2 and 3 dimensions, respectively. For a manifold of arbitrary dimension, the fundamental theorem of calculus can be written in the following form, referred to as the Stokes-Cartan theorem. So the integral over the boundary of the manifold of an n-1 form is equal to the integral over the entire manifold of the exterior derivative of that n-1 form. Just as the exterior derivative is nilpotent, so too is the boundary operator. So the boundary of the boundary is equal to the exterior of the exterior, despite the fact that the boundary is not equal to the exterior. We can complete a complex chain by the action of the exterior derivative acting on forms. We can use the exterior derivative to define the kth DRAM cohomology group via the quotient of a kernel of the exterior derivative acting on k forms modulo the image of the exterior derivative acting on k-1 forms. In R3, the DRAM complex yields the following map. We can see the process of the gradient occurring here, as well as the process of the curl. And then in the space of 3 forms, they can be integrated to yield the notion of divergence. To take then the exterior derivative beyond that point gives us 0, since there is no boundary of any dimension higher than 3 in R3. So the boundary of the boundary then leads us to 0 once you go past the space of 3 forms. So now that we understand the operator that raises the degree of k forms, we can consider an operator that lowers the degree of k forms called the codifferential, and I use the word k form and n forms interchangeably here. Pardon me for that. We can express the codifferential of k forms in terms of the exterior derivative in the Hodge dual, which relies on a symplectic form or Riemannian metric. The codifferential features the following chain complex related to how forms change under integration by parts. For functions, the Hodge dual operator with the exterior derivative forms the Laplacian. We can also generalize the Laplacian further than before with these more powerful operators. One example of such a generalized Laplacian is the Laplace-Beltrami operator, also called the Hodge Laplacian, which operates on Riemannian manifolds. This happens to be equal to the square of the Hodge Dirac operator. Finally, we can consider the Hodge Laplacian acting on a scalar function f. That equals the exterior derivative of the codifferential of f plus the codifferential of the exterior derivative of f. But for a scalar function, the first term cancels out, leaving us only with the codifferential, or in other words, the co-curl of the exterior derivative of f. But that equals the negative Laplace-Beltrami operator. Given that we have covered the Hodge Laplacian in terms of how exterior derivatives operate alongside codifferentials, we can consider it also in terms of complex valued manifolds. If we allow our forms to take complex values in the case of holomorphic manifolds, then we can decompose the exterior derivative of a complex PQ form, which we shall call zeta, into a sum of complex analytic and non-analytic derivatives called the holomorphic and anti-holomorphic Dolbeault operators, respectively. The nilpotence condition can now be expressed as follows. This allows us to define the Dolbeault Laplacians on complex manifolds. The Hodge Laplacian can now be written in terms of the holomorphic and anti-holomorphic Dolbeault operators. Oftentimes, there will be a scaling factor or a normalization coefficient, depending on how you are working within your theory. We can expand the terms and express the operator acting on our PQ form, zeta. Note that zeta can be decomposed into a sum of harmonic, exact, and coexact forms. This is called Hodge decomposition. Our next step is to consider the cohomology groups that we can form with this new information. Recall the kth DRAM cohomology group, written in terms of the kernel of the exterior derivative acting on a k form modulo the image of the exterior derivative acting on k-1 forms. We now have analogous holomorphic and anti-holomorphic cohomology groups called the Dolbeault cohomology groups, where we have the holomorphic Dolbeault operator, the kernel of it, acting on PQ forms modulo the image of that holomorphic operator acting on P-1 Q forms. For the anti-holomorphic variation, we have the kernel of the anti-holomorphic operator acting on PQ forms modulo the image of the anti-holomorphic operator acting on PQ-1 forms. We are in a position to formulate the Stokes-Cartan theorem as a fundamental theorem of complex analysis. However, as we have seen before, the sum of holomorphic and anti-holomorphic derivatives simply yields the exterior derivative. It turns out that even the theorems of complex analysis are special cases of the Stokes-Cartan theorem. This also shows us that Dolbeault cohomology is a special case of DRAM cohomology. In geometric calculus, we can define both interior and exterior derivatives on multivectors as follows. Notice the wedge product can be re-represented in terms of the imaginary unit times cross product. If f is a vector-valued function, then we can combine these derivatives into a vector derivative that in specific contexts is also referred to as the space-time derivative. If f is the Faraday bivector field, we obtain the unified Maxwell's equation for electromagnetism. So we already have all of electromagnetic theory in one equation. Let's see if we can add gravity to the mix. We can reconsider our notion of codifferentials, or the co-curl, from earlier and apply this within the context of a vector coderivative D. This is then the interior and exterior vector coderivative. Since the codifferential relies on a Riemannian metric, the vector coderivative of the Faraday bivector field induces a gravitational field from the action of electromagnetic dynamics and vice versa. This yields the generalized Maxwell equation for curved spacetime. This turns out to be a special case of the Yang-Mills equation, which, in full form, extends our logic to handle a wider class of non-abelian gauge fields in spacetime, non-abelian referring to those algebraic structures that are inherently non-commutative. We can forge a Levi-Civita connection condition by considering the co-curl of a coframe in terms of the metric tensor G. So we start out with this torsion tensor here. That's not the Levi-Civita condition at all. We need that to go to 0. So when that term goes to 0, we then obtain the Levi-Civita connection, which is implied by the case where the covariant derivative of a metric is also 0. The directional coderivative of the coframe can also be expressed in terms of these connection coefficients. Once again, if the connection coefficient goes to 0, we see once again that the derivative of the metric tensor is equal to 0. That is the Levi-Civita condition. By differentiating again, we can form a Lie combinator acting on our coframe, yielding the Riemann curvature tensor components. We can express this curvature equation as the following. For a differential form omega, we wish to consider a derivation operator that incorporates a manifold's curvature in addition to the exterior derivative, which is written in terms of a Lie bracket, establishing the exterior covariant derivative. So we have the exterior derivative of omega plus the Lie bracket commutator. Written in terms of a tensorial zero form, phi, the exterior covariant derivative is not nilpotent. And in general, this is true. F is the field strength tensor in terms of the curvature 2 form omega. So we can represent F as rho of omega. So the field strength tensor in this form is the representation of the curvature 2 form in the general linear algebra of vector spaces, GLV. We also see that the exterior derivative is a special case of the exterior covariant derivative where curvature goes to 0. We consider a linear map of the exterior covariant derivative given a real valued vector bundle mapping A to M with the connection del. We raise our space of forms by 1, as usual. We can see from here that the covariant derivative alone is yielded by the special case where k equals 0. So to finish our overview of the exterior covariant derivative, we will consider one last property. If F is a curvature 2 form of a connection on a principal bundle, we can write it locally as follows. This is written in terms of the curvature 2 form components acting on the exterior product formed by differentials. In F sub mu nu, the components of the curvature 2 form are given by basically what is the Faraday tensor components plus a commutator. In such a case, those would be gauge potentials. The Bianchi identity is none other than the fact that the exterior covariant derivative of the curvature 2 form is 0. We can write it in tensorial form as follows. We want to expand the power of derivations to more general mathematical spaces now. A good start is to consider either functions or functionals in normed vector spaces, such as Banach spaces that are potentially infinite dimensional. A common example of such a space is a Hilbert space. A complex Hilbert space H can be decomposed into a direct sum of infinite separable subspaces. In higher physics, such as in quantum field theory, one can consider infinite copies of both symmetric and antisymmetric single-particle Hilbert spaces composed with a direct sum of tensor products of those Hilbert spaces, and these are called Fock spaces. This is a great way to organize all the degrees of freedom for a multi-particle system, built up from single-particle Hilbert spaces. S sub nu is the grading operator, because this can be, once again, either symmetric or antisymmetric. We will split them up accordingly. In this case, we just get a symmetric tensor product space. And our formulation looks about the same as it did before. Because we still rely on the tensor product, it's only graded now to be symmetric. However, we don't have to use S minus on the tensor product because we can just represent it. Instead of the nth tensor power of the Hilbert space, we can now use the nth exterior power of the Hilbert space, and that yields an exterior product space. In terms of the wedge product, no less. While it's a fun task to construct various Hilbert spaces and Fock spaces, there are many other normed vector spaces we could have considered. For such spaces, we can begin considering derivation operators, such as the Frechet derivative. For a functional f that maps x to the reals, a Frechet derivative at x naught is a continuous linear map L mapping x to the reals such that the limit as h approaches 0 of f of x naught plus h minus f of x naught minus this term L of h divided by the norm of h sub x must equal 0. In a finite dimensional space, the Frechet derivative is a standard derivative. The Frechet derivative can be written as a generalized uniform directional derivative as follows. We can likewise consider a derivation operator that does not require that the limit exists uniformly for all directions, and this is called the Gateaux differential. For locally convex topological vector spaces A and B, where U is a subset of A and is open, and F maps U to B, the Gateaux differential of F at U in the direction x is then given by the following. In general, a function can be described by the following map. Say we have a variable at x naught mapped to f of x naught. We can then generalize this map to what we call a functional, where we map a function f to a location f of x naught. A linear functional on a vector space V is given by the following. Linear functionals of this form satisfy both the Cauchy functional equation for additivity as well as the property of homogeneity under scalar multiplication. So phi of x plus y is equal to phi of x plus phi of y. It is then also true that phi of the constant alpha times x is equal to that constant alpha times phi of x. In essence, we have already considered examples of functional derivatives when we covered Frechet derivatives and Gateaux differentials. We can form functional derivatives by varying a functional f. However, we will focus on the variation of an action functional s. This action functional is given by the following. So it's the Lagrangian of fields and its derivatives and the basis vectors. Under first order variation, we obtain the following. We perform integration by parts on the second term of the sum. This will yield a boundary term, as well as another integral. But since we send the boundary term to 0 by the definition of taking the variation of an action, we now obtain the following form for the variation of s. The integral equals 0, so the integrand is equal to 0, yielding the covariant Euler-Lagrange equation. This equation is the functional derivative of the stationary action s in respect to the field phi. One example that can be yielded from this equation or this functional derivative is something called the geodesic equation. Our purview of derivation operators has expanded to such a degree that we can essentially encode all of modern physics in a single operator acting on a functional. The study of how this functional is minimized by the derivation operator acting on it yields the equations of motion for any given system for free, though free does not necessarily mean easily accessible. By this I mean that nothing is taken for granted in functional analysis, which is an inherently rigorous and challenging field of math. In general, the Dirac operator acting on a spinor field psi is of the following form, in terms of Dirac gamma matrices, gamma. I times the gamma matrices times the partial derivative of psi. This is the ordinary Dirac operator. This can be generalized to a curved spacetime with gauge field terms when the partial derivatives are replaced by covariant derivatives with the additions of both spin and gauge connections. And the components are then given by the following. The Dirac operator can be squared to yield the following. The commutation relation here gives us 2 times the inverse metric tensor. And the commutator here of the actual components of the covariant derivative, in this case with these connections, yields the Riemann curvature tensor components acting on the gamma matrices plus the gauge term for the field term, or the field density. Due to the overwhelming power of the Dirac operator, even under simplified connection conditions, many geometric generalizations of derivation operators are colloquially referred to as Dirac operators. In prior videos, I have emphasized the importance of the Dirac operator for non-commutative geometries in terms of a mathematical gauge theory for quantum fields and gravity. The Atiyah-Singer index theorem tells us that for an elliptic differential operator on a compact manifold, the analytical index of that operator is equal to its topological index. This is just a complex way, really, of saying that the data related to the dimension of the space of all possible solutions is equal to the set of topological data. If we allow psi to be a kernel of an elliptic differential operator D and allow capital theta to be its co-kernel, the analytical index of the operator D is then given by the following, where the dimension of the kernel of the elliptic differential operator minus the dimension of the co-kernel of that operator is the index. However, the co-kernel of the elliptic differential operator is equal to the kernel of its adjoint, allowing us to simplify this as follows. The Atiyah-Singer index theorem can also be intuited and understood by a heat kernel equation. This is what allowed us to express the fundamental principles of modern physics in terms of a heat kernel expansion with Seeley-DeWitt coefficients in a prior video. To finalize this section, we will reconsider our spectral triple for non-commutative physics that allow us to encode both gravitational field theory as well as quantum field theory. The spectral triple A, H, and D, where A is an operator algebra, H is a general Hilbert space, and D is the generalized Dirac operator. For our specific non-commutative standard model, we use the space of all infinitely differentiable functions on a Riemannian manifold M, that being C infinity of M, and then take the tensor product of that with the complex numbers plus the quaternions plus the rank 3 complex matrices. The derivation algebra of the complex numbers is trivial, helping us to encode U1 symmetries. Whereas the derivation algebra of the non-commutative quaternions is non-trivial, and it is isomorphic to SO3, the Lie algebra, as well as the Lie algebra SU2. So SO3 is then our real valued complex, it's our real valued representation, whereas SU2 is then for complex representations. The derivation algebra of M sub 3C is then isomorphic to the general linear algebra of 3C. So that's GL3C. The Hilbert space is equal to the space of all square integrable functions L2 of M and S, which itself is a Hilbert space, tensored with the finite degrees of freedom, which is a collection of finite Hilbert spaces for fermions. The Dirac operator is given by the geometric part acting trivially on the Hilbert space, which in that case is indicated by it being tensored with the identity element 1, plus the chiral element gamma sub phi tensored with the internal degrees of freedom. This ensures that chirality remains stable in error field theory. The spectral action principle is of the following. The trace term is given by the trace of E to the negative squared Dirac operator divided by a scaling factor squared. We recall that we focused on performing an asymptotic expansion of the trace term to yield gravity, gauge fields, and the Higgs field using the Seeley-DeWitt coefficients. We decided on n equals 4 for our dimension constant due to spacetime, yielding the following beautiful series. F sub 4 minus k is a modified Mellin transform of f of u at 4 minus k. And that's the integral from 0 to infinity of f of u times u to the 3 minus k, all integrated in respect to u. We chose a cutoff function e to the negative u in our last video, leading to the gamma function f4 minus k. We can show each term explicitly here. The index of the Dirac operator, since it is a differential operator of Fredholm type, goes to 0 for odd dimensions. An operator with a topological index that does not vanish for odd dimensions is then called a pseudo-differential operator. The a sub 0 component acting on the squared Dirac operator corresponds to the cosmological constant term in general relativity, related to the volume of our manifold of spacetime. A sub 2 then, the next even term, corresponds to the Einstein-Hilbert action, where R is the Ricci curvature scalar. G here is the determinant of the metric tensor. A sub 4 then leads us into the field theories. In this case, the trace of f sub mu nu times f upper mu nu plus the covariant derivative of phi with its absolute square minus v of phi, which is the potential. This is all integrated in respect to four-dimensional spacetime. S sub mu nu times f upper mu nu are the Yang-Mills gauge fields for the Lie group G, which is equal to SU3 cross SU2 cross U1, generated by the Lie algebra little g, which is a tangent space at the identity of the manifold G, which is equal to SU3 plus SU2 plus U1 as a direct sum. These help formulate the gauge fields in our standard model particle physics. The covariant derivative acting on phi here, then squared, and v of phi are respectively the kinetic and potential energy terms for the Higgs field. We wish to consider derivation operators for quaternionic functions, bringing us to the realm of hypercomplex differential analysis, or hyper-holomorphic analysis. Quaternions form a non-commutative algebra, so a quaternion Q can be expressed by the following. I squared is equal to j squared, and that's equal to k squared, all equaling -1. If I times j equals k, its anti-commutativity implies that j times I equals -k. The same then follows for the rest of the multiplications. Accordingly, the quaternion conjugate is given by the following. Due to non-commutativity, taking the derivative of a quaternionic function from the left is not the same as taking the derivative from the right. As a result, we can establish left and right derivation operators. The left and right Fueter operators are expressed respectively. The conjugate Fueter operators, both left and right, can then also be expressed as follows. The composition of the left Fueter operator with its conjugate yields the four-dimensional Laplacian. Written in terms of base of elements E sub u of a Clifford algebra CL4 satisfying E sub u times E sub nu plus E sub nu times E sub u equals 2 times the Kronecker delta function, we can write the Fueter operator D as shown. The Fueter operator D is just a four-dimensional Dirac operator. So quaternionic regular functions in hypercomplex analysis satisfying df equals 0 can be viewed as monogenic functions in Clifford analysis. We can consider the Cauchy-Fueter chain complex, which not only generalizes the Dolbeault complex to quaternionic functions, but turns out to be a specific instance of the Clifford complex. We will write it in terms of a spinor bundle S over R4 associated with the spin representation of spin 4, the universal double cover of SO4. As well as the kth exterior power of a cotangent bundle with degree k differential forms of sections, denoted by lambda k. The Cauchy-Fueter chain complex for R4 can be written as follows. While notions of commutativity may indeed be lost, there is still one property that the Fueter operators retain that yields familiarity, and that is the property of linearity itself. So let phi and psi be elements of the space of infinitely differentiable smooth functions. In terms of the Euclidean space R4 and the spinor bundle S over R4, tensored then with the kth exterior power of the cotangent bundle of degree k differential forms as sections. The fact that this operator is linear may seem trivial. However, we will eventually reach a scenario where linearity itself is lost, leading to new heights of abstraction. We will cover an example later, so we shall continue to motivate an appreciation for linear operators while we still have them. Before moving on to our next derivation operator, we will extend our Fueter Dirac operator to operate on the Dirac gamma matrices themselves, extending our representation to spin 3-1 and CL 3-1. Spin 3-1 is a universal double cover of the Poincare group ISO 3-1 for four-dimensional spacetime, giving us all the degrees of freedom needed for a quantum field theory of spinors. We choose 3-1 instead of 1-3 because we chose a mostly positive Lorentzian metric signature for spacetime throughout this presentation. This gives us the most famous form of the Dirac operator that people are familiar seeing within the context of Feynman slash notation. We will then express the Dirac gamma matrices in terms of the Pauli sigma matrices. The commutation relations for these Dirac gamma matrices is yielded by 2 times the inverse Minkowski metric tensor times the four-dimensional identity element. This yields 16 basis elements in CL31, the Dirac algebra. Whereas for the sigma matrices, we have the commutation relation yielding the Kronecker delta function times the two-dimensional identity element. That yields 8 basis elements in CL30, the Pauli spin algebra. This is the operator that establishes the Dirac equation for a spinor field psi, such as fermions with a mass m. We'll expand that Feynman slash notation. Note that we are also writing this in natural units. We can extend the concept of derivations to conformal field theories as well. We start with the Laurent polynomial algebra. We can form derivations on this algebra to form the Witt algebra, an infinite dimensional complex Lie algebra spanned by the following generators that form vector fields on the complex plane using partial derivatives. The generators for the Witt algebra obey the following commutation relation. In quantum field theory, we can introduce a central charge C with appropriate factors that acts as a conformal weight, effectively accounting for anomalies that appear in the theory itself. This unique central extension of the Witt algebra is called the Virasoro algebra. The Virasoro operators L sub n can be viewed as generalized derivation operators that act on fields with a conformal weight H. Let's distribute phi, and then expand the partial derivative operator that we are familiar with from earlier, showing a similar structure to the covariant derivative. And here's the conformal weight term written out explicitly. We now consider a vertex operator algebra composed of a vector space of states V, a linear map Y that takes the tensor product of two vector space of states and maps them to V of Z, a vacuum vector 1, which is the identity element, and a conformal element omega, where V of Z is the space of all formal Laurent series with coefficients in that vector space. The formal distribution Y of omega Z is what we call the vertex operator, which is also referred to as the weight 2 Virasoro field capital L of Z. We have now generalized our notion of derivatives to derivation algebras in terms of vertex operator algebras. So by now it should be fairly obvious that there's not really a single true derivative operator, as it really seems like we can continue to expand upon this idea pretty much endlessly to form more powerful operators. Many have been shown so far. So really, take your pick. Is it the exterior derivative? Is that the true derivative? Is it the exterior covariant derivative? What about the variation operator? Does that not truly give you back all the derivatives that you can get over regular functions as well as functionals? Really, the choice is up to you. Q derivatives, also called Jackson derivatives, stem from the study of quantum algebras and quantum calculus, a realm of multiplicative parameters, while H derivatives, on the other hand, also called finite difference derivatives, stem from discrete calculus in general, a realm of additive incrementations. Both of these derivation operators establish the notion of differentiability without relying on the concept of a limit whatsoever. In fact, ordinary derivatives are limits of these more generalized operators. Consider the definition of the H derivative for a real value function f and a non-zero real number h. Well, that's just the regular definition of a derivative without this extraneous notion of a limit. And indeed, by taking the limit as h approaches 0 specifically, we obtain the ordinary derivative. The numerator of this finite difference formula is called the forward difference operator. The backward difference operator is then given by the following. We can compose these to form the central difference operator. For differences of order n, these formulas can be generalized with the help of binomial coefficients. So the nth forward difference, for example, of this case, f of x, is equal to the sum as k ranges over 0 to n of negative 1 to the power of n minus k times the binomial coefficients n choose k times f of x plus kh. This goes on now also for the backwards difference as well as the central difference. Interestingly enough, the coefficient for each value of k is given by the rows of Pascal's triangle. This leads to the study of signed and unsigned Stirling numbers. We will now consider the Q derivative. We'll go ahead and factor that in, or distribute that x in to give qx minus x in the denominator for a specific reason. By taking the limit as q approaches 1, we obtain the ordinary derivative, but that's not why we showed it this way. It's just worth knowing that as an aside. A q derivative of order n can be expressed by the following, where lambda equals n minus k, and the qth analog of n choose k forms the q analog of the binomial coefficients, formerly called the Gaussian binomial coefficients or Gaussian polynomials. And it's quite a complicated formula. I'm sure you can agree. I don't think anyone wants to really sit down and do this on paper right now. An important generalization of the q derivative is the beta derivative, defined in terms of a strictly monotonically increasing continuous function beta of x, where beta x is strictly not equal to x. So the q derivative then is the unique case of the beta derivative where beta of x is set to q times x. We can obtain the ordinary derivative by taking a limit on a particular condition of the beta derivative. So the limit of the beta derivative of x as q approaches 1 is equal to the ordinary derivative of f in respect to x, given that beta of x is equal to q times x. Finally, we can generalize further to the study of differential post-quantum calculus in terms of two formal variables p, q, establishing the post-quantum derivative. The fundamental theorem of post-quantum calculus can be written as follows. To understand the fractional derivative, a real or complex value derivative of non-integer order, we must first consider the Riemann-Liouville fractional integral. First, however, we develop the general fractional integral operator. If f of x is defined for x greater than 0, we can define the integration operator j as follows. J of f of x is equal to the integral, ranging from 0 to x, of f of t, integrated in respect to t. Squaring this yields a double integral, which is a single integral from 0 to x of j of f of t, integrated in respect to t. Cauchy's formula for repeated integration can then be yielded by the operator jn. We can extend this formula to handle complex non-integer values, changing our factorial function into the gamma function as well. This extension to Cauchy's formula of repeated integration is called the Riemann-Liouville fractional integral. We can check that this gives us back the original integral operator by choosing alpha equals 1. So we have 1 over the gamma function of 1, but that, of course, the gamma function of 1 being 1, gives us 1 divided by 1, so that term just cancels out. We're then left with the integrand inside that integral being x minus t to the power of 0, so that just goes to 1, leaving us with the integral from 0 to x of f of t dt, the original integral j of f we started with in the first place. Now we have the freedom to consider interesting cases, such as taking a half integral. The gamma function of 1/2 is equal to the square root of pi. We can now express the Riemann-Liouville fractional derivative d alpha in terms of the integral operator above, establishing a special case of what's called a differintegral operator. This is not the famed differintegral operator that would normally be shown. This is a special case of it by how we're operating with orders of differentiation and integration, respectively. By flipping the differentiation and integration, we form the Caputo fractional derivative. These operators are already useful for stochastic processes such as fractional Brownian motion, but there are other derivatives that are specifically geared for stochastic processes. Consider, for example, the infinitesimal change of a smooth functional f of a Brownian process w due to an infinitesimal perturbation epsilon h in the Brownian path at a given time t, yielding the Malliavin derivative. A rigid understanding of this specific derivative is beyond the scope of this video, but hopefully you can begin to understand that fractional and stochastic calculus features entire classes of derivation operators on their own that generalize all of the classical operators we have seen before to unconventional domains. There are indeed mathematical spaces where both classical and fractional differentiation are still insufficient. One such example is given by the study of fractal geometry. A Hausdorff dimension D describes the roughness or irregularities of fractal objects, generalizing the concept of dimensions to non-integer values. The Hausdorff measure HD generalizes the notion of a Lebesgue measure for non-integer dimensions. If we allow x and rho to be a metric space, S be a subset of x, delta greater than 0 being a real number, and allow phi of u to be the diameter of a subset of x, we define the operator h of d sub delta by the following infimum equation. So we grade the diameter of a subset of x by raising it to the dth power, the Hausdorff measure dimension, the Hausdorff dimension d itself. We raise that sum from k equals 1 to infinity such that the diameter of the subset of x itself is less than delta. The Hausdorff measure of any subset S is then given by the following limit. Where we take the limit as delta approaches 0, we just get back the standard Hausdorff measure. This is the information we need to consider a fractal derivative in respect to a spatial variable. The Hausdorff derivative of a fractal space function x of lambda, where lambda is a spatial variable and alpha is the fractal order, generalizes the fractional derivatives shown earlier by taking a derivative of a function in respect to the Hausdorff measure of a fractal space. Delta lambda indicates the infinitesimal spatial displacement that is measured using the Hausdorff measure HD. This derivative is useful for modeling processes involving irregular geometries. Let's consider the classical heat equation for a diffusing substance x of lambda T, where d sub c is the diffusion coefficient. We see here just the Laplacian, but by replacing that Laplacian with the Hausdorff derivative, we show that the rate of diffusion depends on the fractal dimension of the space in which that diffusion is occurring. So we generalize to the case of diffusion in a fractal medium. If we want to understand how fluid or heat flows through an object with a cracked surface, or say analyze complex behaviors in financial markets to make predictions on price movements and high-frequency trading, the Hausdorff fractional derivative extends our ability to perform differentiation even in cases where chaos itself inherently underlines the chain of logic. A differential graded algebra, as the name suggests, combines the concept of a differential with a graded algebra. Provided that we have an idea of how differentials operate by now, we should instead begin this section by motivating our focus on the theory of graded algebras, for which the notions of derivation or deformation can be imposed upon them. Letting K be a field or a ring, a graded vector space V sub G over K is a direct sum of subspaces indexed by integers. By equipping this graded vector space with a bilinear associative multiplication operator, mu, say, for example, that maps the tensor product of V to V, such that mu of the tensor product of Vm and Vn components is a subset of V to the power of m plus m, we then form a graded algebra A sub G. One of the most common and powerful examples of a graded algebra is the infinite dimensional tensor algebra T of V. In this example, and especially in this expansion of the direct sum of the tensor products of the vector space V, we see that K is the base field. Whereas in the Fock space, when we were actually working with the tensor product that had a symmetrization operator acting on it, we had a specific field C, the complex numbers, but this is more general. So by grading this further to distinguish between symmetric and antisymmetric parts, we indeed form a Fock space. A graded derivation of degree n is a linear map D mapping A back to itself that shifts the degree of an order m graded algebra by an order of m plus n. By considering the case where m equals 1, and where, of course, D is nilpotent, we form a differential graded algebra. It is a triple, A, mu, and D. A here is a direct sum of components A to n, where n is guided over the integers. Mu is the graded associative multiplication. D is the nilpotent differential operator, such that the exterior of the exterior is 0, that increases the degree by 1. Nilpotence ensures that the differential operator turns A and D into a chain complex. The nth cohomology group of a differential graded algebra is then given by the closed elements, which are elements of the kernel of D of the graded algebra modulo its exact elements, which are elements of the image of D. This chain of logic generalizes DRAM cohomology itself, and can itself be further generalized to cases such as the Lie algebra complex, the singular chain complex of a topological space, the causal complex for general commutative algebras, or to deformations of even more general associative algebras via Hausdorff homology. Quasi-derivations allow us to consider an extension to differential graded algebras for cases where a system may not be a strict derivation. Consider the non-associative Lie algebra G. A quasi-derivation of G is a map Q that takes G and maps it back to itself, such that the following holds. The unit term of interest here is phi of x and y. However, we are allowed to relax the conditions of the Lie bracket at will. Phi of x and y is a bilinear map that measures the failure of Q to be a strict derivation by distinguishing between its behavior on the Lie bracket compared to that of what would be expected of an ordinary derivation. This is then called a deformed Lie algebra. By weakening the properties of the Lie bracket, we form a quasi-Lie algebra. A quasi-derivation is then an exterior derivative for deformed algebras, effectively generalizing all derivation operators we have seen thus far. An operand O is a collection of sets, such as, say, sets of graded vector spaces, like we talked about earlier. labeled O of n, where n indicates the number of inputs. The differential graded algebra A sub g from our last slide can be extended to the concept of an algebra over an operad theta sub n by the following bilinear map. So in this case, we're taking the tensor product of the operad with the nth tensor power of the differential graded algebra, and that maps to the differential graded algebra. Algebras of an associative operad are associative algebras, while algebras of a commutative operad are associative commutative algebras. The algebras of Lie operads are then called Lie algebras, so on and so forth. Notice, however, that we have to assert notions of associativity and commutativity at will, and we also, again, as I said, can relax the properties of the Lie bracket at will and then use phi of xy, the bilinear map, to measure the extent to which Q is no longer a formal derivation. So really, this all hints towards the study of a more general non-associative calculus. Our final destination on the path to generalizing derivation operators comes from the study of higher categories, from which everything we have covered ends up being a tiny portion of a unified category. A category C consists of a collection of objects, such as vector spaces, groups, rings, etc., where for each object, say A and B, there exists a set of morphisms, which are essentially guided arrows from A to B, denoted by hom sub C of A and B, where a homomorphism is a map that preserves the structure of any two objects of the same type. For morphisms F that map objects A to objects B, and G that map objects B to objects C, there exists a composite morphism, G composed of F, that maps A directly to C. For all composable morphisms F, G, and H, there exists the property of associativity. And this is a very generalized composition product. Lastly, in order to have a proper category, we need the final ingredient of the identity element. That being, for every object A, there exists an identity morphism, the identity sub A mapping A to itself for all morphisms F that map A to B, that is a universal solution to the following equation. Before getting into transformations of categories, we must consider the idea of a functor. A functor generalizes the notion of a function. In fact, it generalizes the very idea of homomorphisms. A functor F that maps categories C to categories D is a map that takes any object A that is an element of a category to another object F of A that is an element of another category. It also brings any morphism F that maps objects A to B to another morphism F of F that maps F of A to F of B. Since functors are morphisms in the category of categories called a two-category, they also obey the composition and identity laws of all these other features within the categories. We can try to argue that this is just a generalization of linear algebra in functional analysis, but that would be a highly insufficient understatement. If the entire notion of a vector space and the rules of composition that can exist for any element of a vector space forms a single category, then all of linear algebra is then contained within a single category, which we can call V or vect. This means all of linear algebra is an infinitesimal single subset of the theory of categories. If vect is a category of objects defined as vector spaces over a field K, then morphisms in this case are what we refer to as linear transformations. We need a bifunctor for multiplication, which in this case would be a bilinear map called the tensor product, and this maps the product of vector spaces to another vector space. More generally, the tensor product is a bifunctor. This leads us to generalize the notion of linear transformations from linear algebra to the realm of categories, encapsulated in the idea of a natural transformation. Given two functors f of g that maps the category C to the category D, a natural transformation eta that takes the functor f to the functor g assigns to each object A that's an element of a category a morphism eta sub A that maps the functor of the object A directly to the functor of G operating on A, such that for every morphism F that maps A to B in the category, the following diagram then commutes. So to get from f of A to G of B, we can take eta of A from f of A to go to G of A. Then we can take the morphism G applied to F to then go to G of B. Likewise, we could have taken the functor of F directly to go to F of B and then take eta sub B to G of B. An n category extends our notion of categories to n morphisms. So objects are called zeromorphisms. Morphisms between objects are called one-morphisms. But morphisms between morphisms are called two-morphisms. Morphisms between morphisms, or in other words, morphisms between two morphisms are three morphisms, and this keeps going on for n morphisms. In fact, it goes on to infinity morphisms, forming an infinity category, which has morphisms at all levels, where for every pair of n morphisms, there are n plus one morphisms between them, and commutativity and associativity hold at every level, of course up to continuous topological deformation. A continuously deformable functor f can be approximated by a tower of functors, similar to a Taylor series. If this tower converges to the functor, then f is an analytic functor composed entirely of polynomial functors of degree n, called n-excisive functors. Very clearly, this is a generalization of the very concept of Taylor series. Derivatives of functors are generally nonlinear, but they do follow direct rules, such as the chain rule. Let d sub star be the sequence of derivatives d sub n at f, such that n is greater than or equal to 1. The chain rule for the homotopical or continuously deformable composite functor f of g, or f composed with g, is given by the following. So d star acting on the composition of functors f composed with g is the same thing as independently taking d sub star acting on the functor f and then composing that with d sub star acting independently on the functor g. For any infinity category C, its tangent category TC includes all objects that pair an object of that infinity category with an associated tangent vector. Morphisms that induce such pairings yield the abstract notion of derivation itself. Modules are an extension of the definition of vector spaces to rings as opposed to just scalars. The chain complex of operad modules that are formed from the operad we discussed earlier happens to give us a cotangent complex L sub x that incorporates both the notions of classical differentials and derived deformations. The tangent complex T sub x is then the dual of the cotangent complex. So we see here T sub x is equal to the dual of L sub x. All of the classical theory of derivation that we have covered can be contained in a single generalized derivation complex. Given that hom is a homomorphism functor and omega sub x slash k is a sheaf of differentials, this generalized derivative is called the tangent complex at a point P on a derived scheme X, where a scheme generalizes the notion of a solution set for systems of equations, called algebraic varieties, by extending the definition of algebraic varieties to a more general ring instead of integers, similar to how modules extended the definition of vector spaces to rings as opposed to just scalars. So again, it's just the homomorphism group of omega sub x cross k, or slash k, and the operad sub x. This is an infinity categorical generalization of the derivation module that yields derivation algebras. By considering that this is dual to the cotangent complex on a derived scheme, we can also interpret derivations themselves as homomorphisms from the cotangent complex into other modules. For a derived scheme X, we generalize the derivation functor as follows, where M is a module for our operad over the scheme, which brings us in line remotely with the studies of derived geometry and homotopical algebra. The cotangent chain complex is then expressed as the following. Meanwhile, the tangent complex chain is expressed as It would be fair to motivate the study of many of these concepts here far more rigorously, but that would require another video or multiple on its own. So we have taken some shortcuts to express how all of this is connected. Another primary object within a differential category that can summarize the theory of derivation operators is the notion of the differential combinator, an abstraction of the differentiation operation. If K is an endofunctor, a mapping of a category to itself, then a differential combinator D assigns to each morphism F that takes an object A to an object B, it assigns it a differential morphism D acting on F that then takes the endofunctor acting on the object A and then sends it to B. We can consider the category V of finite dimensional vector spaces and linear maps. For linear maps F that map V to W, the derivative D of F takes the product of V with V and maps it to W, and that's given by the following. This results from the fact that linear maps are their own derivatives. For Cartesian differential categories in general, the derivative of a function is described as a morphism in a category, and the fundamental derivative of such categories that is yielded is then the Jacobian matrix itself. When the differential combinator acts on graded structures from differential graded algebras, we can formulate cohomology groups at will, extending into those domains we have shown within this presentation. Since a cohomology measures the failure to resolve geometric data, the derivation operator acts on algebras to express their algebraic and topological information. And in terms of differential forms, we are left with a concept we covered near the beginning when we talked about ordinary derivatives, where we are considering maps between tangent spaces, bringing us all the way back, full stop from the beginning. In this case, we're not just looking at a tangent line, but the more general notion of a tangent space formed from tangent complexes. As a bonus, I will quickly show two more examples of nonlinear derivation operators, just to say that I did indeed at least try to cover a few more at some point during the presentation. The first example is the Navier-Stokes operator. Here, u.del acting on u is our nonlinear term. That's for convection. If u is a probability density, then the Navier-Stokes operator as a whole tells us that probabilities travel across space and time like a fluid. The second example will be the nonlinear Schrödinger operator for a quantum wave function psi. In this case, nonlinearity arises from k times the absolute value of psi squared times psi. It is clear that we should appreciate linearity at all costs, as these nonlinear terms make equations featuring them, such as, say, nonlinear differential equations, extremely hard, if not impossible, to solve. There are, of course, many other derivation operators that exist, but we simply don't have time to cover them all. And in fact, we've essentially shown in this video that there can be infinitely many more. Here's an example of some more that were not covered in this video, and there's indeed more than even what's listed here. But most importantly, we have one last thing to consider. The category cats is a collection of all traits that define an ideal cat, and that can be modeled by the following perfect representation of a pixel matrix. Thank you for watching.